All right, folks, welcome back to Regression Analysis. Looking at our second set of slides. In the first lecture, we talked about simple linear regression where we had only one regressor. In this lecture, we introduce multiple regression. As the name suggests, we'll have more than one regressor in this analysis. Okay, so the model is not different from what we learned from simple regression analysis. This is our dependent variable y, our intercept, the value of y when all the x's are 0, the beta 1 all the way through beta k are our slope parameters, and u describes the error term or the disturbance or the unobservables. So the key difference here is very simple. We are introducing other regressors in the model. So what's the motivation for multiple regression? You remember I mentioned that simple regression is woefully inadequate, except in certain instances where you are using data from an experiment. Multiple regression allows us to incorporate more explanatory variables into the model. You remember the fertilizer and then the yield example where we were only using fertilizer as our regressor. In a simple linear regression model, there was no way we could include information on rainfall, the use of pesticides, and other variables that affect yield. Because we had limited ourselves to simple regression, we had no opportunity to control for other factors. Multiple regression allows us to control for many more factors. It also helps us to take care of the flexible functional form. You remember the issue about the linear parameters and ability to capture non-linearities. So multiple regression allows us, if you plot the data and you see that you need a polynomial function or a quadratic function, multiple regression allows you to include other functions or other forms of the variables to capture the curves or non-linearity that the data which has been plotted may be showing. Okay, so we are able to hold other factors fixed also, and I will talk more about this in a minute. Okay, so consider our return to schooling equation where we try to estimate the impact of additional year of education on wage. Remember, wage is measured in cedis or dollars. Education is measured as years of education, okay, as integers 1, 2, 3, 4. And consider this to be your experience in the labor market, and you comprises of all other factors that affect wage, okay, and are probably unobserved to us. Okay, so as usual, we explain our coefficient. Okay, so there are k of them. So we refer to one of them as j, okay? Beta j means one of the k's, okay? Let me go back to our first slide. You can see we have x regressors. So there's beta 1 all the way to beta k. And if I want to talk about one of them, I will say beta j, okay? Where j is from 1 to k. It could be any of them. So the idea here is that what I meant by holding explicitly fix other factors, okay, that could be in U. Okay, take for example, here our simple regression will have wage is equal to, let's say, alpha 0 plus alpha 1 education plus U. So you run this model and you say, well, if education increases by 1 year, wage will increase by alpha 1, holding other things constant. Okay, and then somebody says, well, you are saying this is the difference in wages if education differs by 1, but you haven't taken into account the work experience of the people in the study. And you say, oh, okay, that might be a deficiency. So let me move away from simple regression, go to multiple regression that allows me to now take care of the experience variable that somebody has just complained about. And therefore now, okay, you will say, well, an alternative of moving from simple to multiple and controlling for other factors is that somebody will say, well, why don't I now go and interview people or look for people who have the same work experience and now come and run a regression of wage on your education? In that case, the issue about experience doesn't arise because you have now gone for people who have the same level of experience. We are saying you don't need to struggle going to town looking for people with the same level of experience and collect data on their wage and education and come and run your model. You don't need to do that. You can just adopt a multiple regression and it allows you to behave as though you went to look for people with the same level of experience. So in a multiple regression, once you include beta 2 experience, that is it. It serves that purpose. So this beta 1 is the impact of education on wage, holding experience constant. In other words, if I take two people with the same level of experience, beta 1 is the impact of education on wage. Okay, if one of them went to school more than the other. So, like I'm saying that you don't need to go and look for people with the same level of experience and come and run a simple regression on their wage and education to take care of the complaint somebody made. It suffices to use a multiple regression. Once you control or put in beta 2 experience, you are essentially behaving like, oh, holding experience fixed. In other words, if I consider two people with the same level of experience, but one of them went to school more than the other, beta 1 is the difference in their wages. Then somebody will say, well, you haven't included tenure as a variable. Or even when you run this one, you didn't control for tenure, how long the guy has been with his employer. It affects his wages also. You haven't included it. You have one option. Go and look for people with the same level of tenure and come and run this model for them. But that's tedious. So we just use multiple regression and include beta 3 tenure. So we have controlled for tenure. In other words, now this means if I take two people with the same level of tenure, the same level of experience, but one of them went to school more than the other, beta 1 tells us the difference in their wages. So that's the beauty of multiple regression. No need to be controlling for other factors by looking for people who satisfy certain condition. Once you throw in that variable in the multiple regression, you are essentially controlling for the effect of that variable. And so you're able to isolate the effect of one of the variables. That is what we are saying, that you can explicitly hold fixed other factors that otherwise could be in the error term. You're able to bring them out of the error term and include them in the model. Okay, you can always ask questions when we meet in person. Let's go on. So the interpretation is the same, okay? There's another concept I want you to appreciate, okay? Remember that over here, we want to study the impact of education on wage, holding other things constant like experience. Okay. So beta 1 is of interest to me, but I reckon that I may not be successful in getting that if experiences impact on education, okay, it's not taken care of. I want to isolate the effect of education on wage. It's possible experience also is having effect on education, and then education is having effect on wage. So in order to get beta 1, there is another way you can think about getting it, and we call it the partialing out interpretation. If you really want to get the impact of education without any form of spillover effects from other variables. So read this slide slowly and think about it. partially out interpretation of multiple regression. One can show that the estimated coefficient of an explanatory variable in a multiple regression can be obtained in 2 steps. Beta 1, which is attached to education, for example, can be obtained in 2 steps. Regress education on other regressors in the model, like experience. So you are doing what? Education will be alpha 0 plus alpha 1 experience. You are running, yes, there is one regressor on all other regressors. Then you collect the residuals. V hat will be what? Education minus what? Education hat, kind of what we know already, like y minus y hat kind of thing. Okay. So how does experience affect his fellow regressor? I am trying to take that part of education which is influenced by experience off it. So experience affects education. I want to take that effect, isolate it, and throw it away, so that what I'm left with is a residual V hat, which is what? Education minus education hat. Education hat is education predicted by experience. So this V hat is education minus the part of education predicted by experience. I want to take that off. So what I'm left with is education minus its part that is affected by experience. So take this. Let's say this is education, the big variable. Part of it is also explained by experience. I want to throw this part away. I want to throw this part away, and I'll be left with something else, which is the V hat. So this V hat is actually part of education, which has nothing to do with experience. That is the point, right? I want to estimate beta 1 hat, the impact of education on wage, but I don't want any part of experience affecting wage to be part of my result. I want entirely a clean estimate of only education. If experience is hidden somewhere or affects education somehow, I want to throw that off so that I'm very sure that it is actually the impact of education alone, not something else like experience having an indirect impact on wage through education. Remember, I'm going to say that holding experience constant, beta 1 is the impact of education. So I cannot be using part of education which is polluted by, in case experience affects it. So although experience is here, it may affect education by itself, because regressors are usually related. Okay. If it's not too clear, we'll talk about it. But read this slide slowly and think about what we are saying. Okay. So 2 steps. Regress the explanatory variable on all other explanatory variables. So regress wage on other explanatory variables in the model. Collect the residuals. Now regress y on the residuals. So I'm going to regress now wage. Remember, wage was not part of the first stage. First stage is only regresses. Think about it. Play this video again. Slow down. Think about it deeply. Now wage will be run on, let's say, alpha 2 plus alpha 3 V hat. Plus an error. Let's call it W. So the only regressor is V hat. What is V hat? I was supposed to write education here, but I've written a V hat. And what is this V hat? It is the education without any impact, any effect of experience. So we are saying that when you get alpha 3 hat here, it is the same as getting beta 1 hat in our earlier regression. Okay, so look at this. Instead of running this regression, instead of running this whole regression, I do 2 steps. I am regressing this on that, collect the residuals, and run wage on that residual. Okay, why does this process work? Okay. It works because of this. The residual from the first stage is part of the explanatory variable that is uncorrelated with other explanatory variables. The slope coefficient of the second regression therefore represents the isolated effect of explanatory variable on the dependent variable. So take it slow again, read it again, and then you get it. Okay, let's take another example. Let's say I'm supposed to run a regression of y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus u. I'm interested in beta 1. So I'm saying instead of running this long thing, 2 steps can be used. First, step 1, the one I'm interested in, take that x1, regress it on all other explanatory variables, alpha 0 plus alpha 1, x2, all other regressors, plus alpha 3, alpha 2, x3, plus an error term, say v. When I run this regression, I'm supposed to be looking for v hat. Okay, I'll collect the residuals. V hat will be what? x1 minus alpha 0 hat minus alpha 1 hat x2 minus alpha 2 hat x3. So that's the first step. Second stage is just regress y is equal to, let's say, delta 0 plus delta 1. The v hat we got the residual from here. So this delta 1 hat will be equivalent to the beta 1 hat you would have had if you ran all this. Okay, excellent. I hope that helps. Okay, so as usual, we try. Okay, so once you establish what multiple regression is, next step is to think of estimation. The idea is the same. The least squares estimators minimizes the sum of squared residuals. And what is our residual? Ui hat. This is y minus what? Y hat. So all these will be y hat. So y minus y hat kind of. And we minimize sum of squared residuals as we've done in simple regression. So remember, in simple regression, it was easy to solve the 2 normal equations. Here, it is usually done by a computer, but we shall show how the setup looks like, okay? So we are minimizing y minus, okay? This summation is just compressing this thing here. Where is it? All this, right? Remember, is beta 1 plus beta 1 x1 plus beta 2 x2. So you can put it in a summation. Okay, so that's what that one is showing. It's a summation. So that's the idea. The summation is here. Y minus beta 0 minus beta 1 xi1 beta 2 xi2 all the way to beta k xik. So there are k regressors, and not only one, k regressors, and then there's one intercept. So if you are counting the betas, there is beta 0 plus beta 1 all the way to beta k. So there is what? This is 1, 2, 3 up to k, and this is 1. So 1 plus k betas. We usually call it P is equal to k plus 1, okay, or 1 plus k. So this is how the setup looks like, okay? And remember our differentiation from the simple regression. It follows the same way. The 2 will come down here. When you're differentiating with respect to beta 0 here, beta 0 comes with a negative sign, which is the one here. You repeat what is in the bracket, set it equal to 0. But there will be k plus 1 equations. Because after differentiating with respect to beta 0, you must do beta 1, beta 2, beta 3, beta 4, all the way up to beta k. That is tedious and not possible to be done manually. Okay, there will be k plus 1 simultaneous equations to solve. This one representing the beta 0 derivative and k of the beta j's. But we can, as mathematicians, we can see how one of them looks like. If you are differentiating one of the k's, like a j, beta j, then as usual, the 2 comes down, negative 2. And remember, when we were doing the simple regression, there was an x outside, the one attached to the particular beta. So that's similarly, if you are differentiating with respect to beta j, then xij, okay, will be out, okay. We'll also be multiplying this. You set it to 0, and then you simplify, okay. This one has been simplified here. This one. So I'm not going to be asking you to derive this particular one in exam. It's a simple one that may show up. But just see what's going on. If you simplify this, look at this. This becomes this summation yi, okay, appears here at the end when they rearrange things, okay. And then this. So it's important to just see what's going on, then we move on. This summation of beta 0 hat is a constant. So you are summing a constant n times. If you sum the same thing n times, it is n times the thing, right? If I sum this 3 times, 2 plus 2 plus 2, okay, I'm summing it 3 times, so the result is what? 2 times the number of times I'm summing them. If I sum this n times, the result is 2 times the number of times. So if you sum a constant n times, it is just n times the constant. That is why you have n times beta 0 here, and so on. You can see what's going on through there. I challenge you, take your time and go through and see how they obtain this second term. Okay. By the way, you must practice this at home and see how they are writing it. So I is for the individual, then there is beta 0. Learn how to write it. There is beta 1, then individual regressor 1. So this can be education. Then beta 2, I'm still talking about the same individual, but now regressor 2, like experience plus. So this is how come beta k x I k plus ui. This is how come you are seeing ij's in the x that over there, like xi and j, because there's an individual and a regressor. Remember this. Okay, so that's why you'll be seeing things like, xi1, xi2, all the way to xik. Okay, interesting. So let's move on. Now, because the derivation was difficult and so on, there is a compact way or a nicer way of presenting derivations in multiple regression, and that is the matrix form. Okay, so in the matrix form, I'm now using bold. This is now bold. It's not faint, right? It's deep white to show we are working with matrices. Okay, supposed to make the derivations or the calculations easier than what we just saw, writing out k plus 1 equations. So Y here is an n by 1 matrix. Look at it, n by 1, Y1, you stack them like vectors. And then X, beta plus U. They are all bold because they are matrices. What is X? X is what? N by P matrix. Beta is what? P by 1. Remember, P is what? There are K regressors, or K beta 1 up to beta K, and then 1 for beta 0. Okay. Now, don't get confused. In some regression books or in your previous classes, they may use K to count beta 0 all the way to beta K. They are counting parameters. Or then they will use an alphabet to represent that. Here, I count regressors separately. There are K regressors, and then I add my intercept. So take your time and get the difference. I am counting my regressors separately. There are K regressors, and then I know there's a beta 0 intercept, and we call this P. So there are essentially, right, P is equal to K plus 1, P elements in the matrices. So look at this, there's beta 1 all the way up to K, and there's a beta 0, so it becomes P. P is what? All this K plus 1. That's why beta is now P plus 1 and not K. U, or this should also be bold. U is also n by 1. 1, 2, 3, so n by 1. And X is an n by P. The rows, there are n rows, okay, n rows, and this way there are P columns, 1, 2, 3. If you can take your time and really understand this, this represents the intercepts. This is the first person regressor 1. Because the first line is for the same person, the number 1 here will be repeated because it's the same individual, but we change the regressor. Regressor 1, regressor 2, all the way to regressor K. Then move to the second individual in the study. The same individual 2 will be maintained. Then you change the regressors 1, 2, all the way to K. And then the nth observation, regressor 1, regressor 2, up to regressor K. Okay, take your time and get these things. Now, one thing to pay attention to, in simple regression, you write a beta before the regressor. But now these are matrices, and they must be compatible, right? Remember, a 2 by 2 matrix can be multiplied by a 2 by something else. The middle terms must make them compatible. Because of that, you cannot write a beta before the X. Once you're in the matrix form, it comes as X beta. Take note and don't change them in an exam or something. It shows that you really know regression and you are a professional. Now, let's go through the minimization problem to solve our beta, the OLS estimators. Let SB be the minimization problem. Of course, we are squaring our errors or residuals, summing them and minimizing. Now, the transition from here to here comes from matrix algebra. I'm going to do only one of them. After that, you are responsible for exploring any matrix representation you see here. I want to show you why